McGraw-Hill and people that made your book.
Action potentials arriving at the presynaptic terminal cause voltage-gated calcium ion channels to open. Calcium ions diffuse into the cell and cause synaptic vesicles to release acetylcholine, a neurotransmitter molecule. Neurotransmitter molecules, acetylcholine, diffuse from the presynaptic terminal across the synaptic cleft and bind to their receptor sites on the ligand-gated sodium channels. This causes the ligand-gated sodium ion channels to open, and sodium diffuses into the cell, making the membrane potential more positive.
In the skeletal
If the
muscle.
membrane potential reaches threshold level, an action potential will be produced.
Okay? Questions about that? And I don't know why. Maybe it's because I was presented the second day. This is the part that students struggle with. They struggle with synaptic transmission. Again, I don't know if it's because, you know, you had time to percolate the first three, and they were all kind of related in a lot of ways. And then we get to this one, and this is different, but not a lot different. We're still talking about voltage-gated ion channels. We're talking about changes in membrane potential. We're talking about exocytosis. You're familiar with that one, where the vesicle fuses with the plasma membrane and dumps a chemical into the space. And then we've had chapter 6, where a chemical binds to an ion channel and opens it. So we're combining all that stuff that we've already learned from our previous chapters. Building. That's why you're not supposed to flush after every test. Any questions? Anything that you don't understand? Now, neurotransmitters, they need to be removed because we cannot keep the ion channel open. We need to remove it. So if we need another impulse, we have to produce another neurotransmitter. We have to put out more. We don't leave the neurotransmitter in place. We've got to get rid of it. So it depends on the neurotransmitter what happens. If we're talking about acetylcholine, it gets broken down by, cleverly enough, acetylcholine esterase. That enzyme name. Or, depends on the neurotransmitter. It may get reabsorbed. It may just float away. It depends on the neurotransmitter. Right now, let's talk about drugs. The insecticides that are called organophosphates, they block acetylcholine esterase. What would happen if we had no acetylcholine esterase? Exactly. So roaches twitch as they die. So do people. The only difference is we're bigger. So that's why the Environmental Protection Agency removed organophosphates from the homeowner market, almost exclusively, not entirely. You can still get malathion, and you can still kill yourself with malathion. So you might have that potential of seeing someone in an attempted suicide, having dosed themselves. If one day you should happen to work with migrant workers, sometimes migrants are not thought of as people, and so they go ahead and spray the field while the migrant workers are in the field. So you may one day see organophosphate poisoning. But we use this therapeutically. There's some drugs that we give that specifically block acetylcholine esterase. If you have a disease called myasthenia gravis, you take a drug that keeps acetylcholine in the synapse longer. If you have Alzheimer's, you take a drug called Aricept. You don't know you're taking a drug called Aricept, of course, because you have Alzheimer's. But what it does is keep acetylcholine in the synapse longer by blocking acetylcholine esterase. All right, there's another class of drugs you may or may not be intimately familiar with. Prozac, Zoloft, and one of the components of Cymbalta. They are selective serotonin reuptake inhibitors, which means they keep serotonin from being pulled back up. into that presynaptic neuron. Keep serotonin in the synapse longer. Serotonin is a mood elevator, so it makes you happy. So that's how Prozac works. And there are many other drugs that affect, again, neurotransmitters. There's another picture. A little bit of a delay. All right. Ooh, look at that. I even have a question on acetylcholinesterase inhibitors. The insecticide class, called organophosphates, inactivates acetylcholinesterase in the synapse. So what is it doing? Good job. Inhibits the breakdown of acetylcholine from the postsynaptic membrane. It does not affect the presynaptic neuron at all. Acetylcholine is still going to be released. But once released, it doesn't get broken down. So it leaves the ion channels open, so the muscles cannot reset. So it doesn't speed them up. All it does is keep the ion channel open. And then there is no reset of those neurons, of those muscles, sorry. So questions about that? Just quickly talk about postsynaptic potentials. All right, now I told you that a neurotransmitter, it's going to open ion channels, but is it going to depolarize or is it going to hyperpolarize? If we depolarize, that's called excitatory, because we're moving toward the next action potential. So depolarize is excitatory. Hyperpolarize is inhibitory, because it's making the membrane even lower below threshold. So it's less likely that we can get an action potential to occur. We're making it even more negative. So when you look at your neurotransmitters at the end of chapter 7, most of them are excitatory, but some of them are inhibitory. And then I've already mentioned this, nicotinic is always excitatory because it always opens sodium channels, which always depolarizes, so then the muscle will contract. Muscarinic is either excitatory or inhibitory. Depends on the tissue. Oops. And that's what makes chapter 9 hard. It's not just more neurotransmitters, it's different receptors that have different responses in different tissue. Slows down the heart, speeds up the gut. So that's what this is addressing. Excitatory postsynaptic potential. Is it going to depolarize or is it going to hyperpolarize?